right, so let's begin. We're happy to have Xueda Wen from MIT tell us about Floquet CFT and beyond.
I will introduce a very simple story called the Floquet conformal field theory. This talk is based on two recent works with collaborator Jie Chang, who is a postdoc at MIT, and Rui Hua is a graduate student in the audience. He's in the group actually. And Yunfei is a postdoc at Harvard. And I will also introduce some works in progress. Okay, so first, let me start from the motivation. So we have seen a lot of studies on Floquet in the literature. But then when we are simply curious if any people have studied the Floquet conformal field theory. We searched the literature and didn't find any exactly solvable setup for conformal field theory. So our motivation is very simple. So no people will study this setup. We are simply curious about what is the author. Okay, this is our motivation. And there are also some mathematical motivation for fun. This is called complex dynamical system in mathematics. So now, if we consider a complex plane. We start from some point. Then we consider a mapping f, map this point to the other point. We do this mapping on and on for many times. Then we can find that this point can either flow to infinity, or this point will simply move locally inside some region. I believe most of us have seen this such kind of plot. So in this plot, if we start from some point in this dark region, when we add this the function for many times, the point here will flow to infinity. In this light region, no matter how many times you add your function on this point, it will simply move locally inside in some local region. So what I want to say is that this pattern depends on the function f. If you change another function f, you will have another very beautiful pattern. But in this pattern, there are only two regions, the dark and the light. They have quite different behaviors. So we are simply curious: is this kind of pure mathematics related to any non-equilibrium dynamics in physics? Okay, this is our mathematical motivation for fun. Okay, so the structure of this talk is as follows. First, I introduce what is Floquet CFT. Then we will I will introduce a simple generalization to the randomly driven CFT and some quasi-periodically driven CFT, and I will also introduce some open question. Okay, so let me first introduce the setup of Floquet CFT. Oh, I forgot to mention Floquet simply means you drive the system periodically in time. That's the meaning of the Floquet here. Okay, so what do I mean by drive the system in time? Here I simply mean we consider a time-dependent Hamiltonian. Here T, capital T is the stress energy tensor in CFT. T00 is nothing but the Hamiltonian density. We simply put envelope function f. This function f is a time-dependent function. Okay, the physical meaning is very simple. We simply deform the Hamiltonian density as a function of time and see what happened for this CFT. Okay, so for the Floquet case, it simply means this function has a period in time t. Similarly, if you consider quasi-periodically or randomly, you simply modify this how this function depends on time. Okay, that's very simple. Okay, so in 1 plus 1D CFT, the Fourier component of this Hamiltonian is composed of a Virasora generator, which satisfies the well-known Virasora algebra. Okay, what I want to say is that it is challenging to solve this problem for arbitrary f. For arbitrary f, it is not easy to solve. But now let's start from some simple choice. We start from some simple choice of f. Once we can understand some simple case, then we may be able to understand some general case. This is our logic. So the simple choice of this f is of this form. We have a plus b times cosine 2 pi n over L times x. Here x is the space plus c. So why I choose this form? Because if you choose this kind of f, you can find the Fourier component of the Hamiltonian is composed of only 3 generators: L0, Ln, and L minus n. Sure, there's an anti-holomorphic part. So these 3 generators form a closed algebra, which is called SL2 algebra. Then it's easier to handle this problem. So
is this problem solved in the time-independent case?
Independent case.
Yeah. It seems already
Sure. If I cannot solve it for the time-independent case, then there's no way to solve it in time-dependent case. Yeah, we can solve it in time-independent case. We have, yeah. Okay. So till now you have seen the general idea of the Floquet CFT. Our ultimate goal is to drive the CFT with the Virasora algebra, which is infinite dimensional. But now, as the initial effort, we will drive the CFT with the SL2 algebra, which is simpler. As we will see, there are already non-trivial features even in this very simple kind of driving. There is some non-trivial feature.
What's the coefficient of the SL2?
Coefficient? What do you mean by coefficient of?
Something like SL2C, SL2R.
Oh, SL2R, sorry. Yeah, SL2R. Yeah. So let's start from a very concrete and simple example. Okay, we only choose our Hamiltonian is time independent. We only have choose 2 Hamiltonian, which we call H0 and H1. So H0 is nothing but a CFT Hamiltonian with uniform Hamiltonian density. Uniform means space. We have open boundary condition here, and H1 is a very simple deformation of the Hamiltonian density, which I choose as sine square pi x over L. This is some very simple choice. I will tell you what happened for some general choice. Okay, we fix the 2 Hamiltonian H0 and H1. We drive the system with Hamiltonian H1 for time period T1, and then we switch to H0 for time T0. We repeat this procedure on and on. Okay, the initial state is chosen as, for example, as the ground state of the H0. You can choose some other initial state. Okay, then let me tell you the result first. Because now I have fixed the Hamiltonian H0 and H1. The only parameter that I can tune is T0 and T1, the time period. So we expect there should be some phase diagram as a function of T0 and T1, right? So it is totally possible. The result is quite trivial. Nothing
Is there a relative energy scale?
Ah.
Is there a relative energy scale as another parameter?
Good. The only energy scale in this setup is the length, the total length of the system, and T0 and T1.
Do you lose any freedom when you fix it like this? Because I could imagine that there is a relative energy scale between H0 and H1.
relative.
Yeah, like h0 is multiplied by 1 and h1 is multiplied by e, and e is another parameter. Like in the previous equation, in the previous slide.
I think you can absorb it in definition of T0 and T1.
Yeah, you can absorb that into T0, T1. Yeah, exactly. So the only energy scale in this setup is only T0, T1, and the total length of the system with a CFT. Okay, so it's totally possible nothing interesting happened in this parameter space, but to our surprise, we found some interesting phase diagram. Let me show you the result first. This is T0 or L, this is T1. We found there are two different phases. So you may ask, what do you mean by different phases in a non-equilibrium setup, right? Okay, how to distinguish two different phases? We simply study the entanglement entropy of half system. We found that in this red region, the entanglement entropy grows linearly in time all the way. In this blue region, the entanglement entropy simply oscillate all the way. It never grows down. So we simply give the name a heating phase and a non-heating phase. Although this is not a good name, as you will see later, but we simply use the name. Okay, because the entanglement entropy always grows. It seems like we are heating the system. We call it heating phase. So at the phase transition, the entanglement entropy will grow like log t growth. Okay, so good. We found some interesting pattern in the phase diagram, but you may ask.
So omega is the same. Omega is the frequency there.
Oh, good. Omega is not the omega is different from the frequency here.
Mm-hmm.
For example, when we use high frequency driving here, omega is only depends on L, the total length of the system. Yeah,
So omega actually depends on different points. Different point omega is not the same.
Right. Okay, there is some interesting phase diagram. You may. Okay, before I introduce why we have such phase diagram, let me. If we change this fx to some other choice, for example, a plus b sin, you can tune the parameter arbitrarily you like. You can get a different phase diagram. Okay, but the common feature in this different phase diagram is that they only have two phases. One is heating phase, one is non-heating phase. Okay, but yeah, this is the result. But what is underlying this phase diagram? I will tell why we have this phase diagram. Okay, this is a little bit technical, but what I want to say is that in the calculation of the entanglement entropy, essentially we are calculating the correlation function. When we drive the system, we can track how the operator. We can choose some primary operator in the CFT. When we drive the system, we do some unitary transformation. We act it on the operator, and we observe how this operator move in the complex plane. Or we can find with SL2 driving. This operator will move on a circle with the function we call it f. F acts on the point here. It will move along the circle. This transformation is very simple. It is called Möbius transformation. We have AZ plus B over CZ plus D. Z is the coordinate of the operator. Okay,
Why does it move rather than spreading out?
It will not spread out because this is integrable. Right? CFT, this is CFT. We only use the Virasora algebra. Yeah, so this operator will always move in a definite, fixed way. It will never grow.
Yeah, because you choose a very special H1.
Yeah. Actually, I think as long as the H1 is chosen as the deformation of the Hamilton density, it will always move in this way. Yeah, but no, this it will never grow up. If you add some non-integrable terms, it will become fat. Okay.
But this have nothing to do with this integral, non-integrable. So yeah, the spread of the operator is related to OXT. Yeah, OXT is always a very complicated operator. If you think in terms of the Schrödinger picture,
Okay.
it's always a very complicated operator. Yeah, but you just hide the complication in the location of the
Yeah.
in the space time.
Right. Yeah, here we know the location of this operator. I mean, we are sure how this operator, how the location change the function time. Yeah, it obeys a Möbius transformation. So for each Möbius transformation, we can have a 2 by 2 matrix, which is SL2C matrix. This matrix is the algebra is SL2R, but the matrix itself is SL2C. So now this problem is reduced to a very simple one. If you drive the system, you simply multiply different SL2C matrices one by one. Then you can check how the operator moves on the circle. You can find, okay, in the Floquet CFT here, there are in total 3 kinds of Möbius transformation, which are called elliptic, parabolic, and hyperbolic. There are only 3 kinds of Möbius transformation. So they correspond to the non-heating phase, and the phase transition. Yeah, here is simply the formula. The intuitive picture is as follows. If we have if this 2 by 2 matrix is a elliptic transformation, now as a function of time, we see how the operator move on the complex plane. For the elliptic transformation, this operator will simply oscillate in time on the circle as a function of time. If for the hyperbolic transformation, the operator will flow to some fixed point exponentially in time. So right here, I didn't plot the parabolic transformation. It will also flow to some fixed point, but power law behavior, similar to this one. So as a short summary for the 3 kinds of Möbius transformation. For this oscillating phase, the Möbius transformation have 2 fixed points, which are not on the circle. So the operator will always oscillate on this circle. It will never flow to the fixed point. For the hyperbolic, for the heating phase, there are 2 fixed points. One is attractive fixed point, the other is repulsive fixed point. So the operator will always flow to some attractive fixed point. At the phase transition, you can find the 2 fixed points will first merge on the circle at the phase transition, and then split to 2 fixed points on the circle. This is the underlying mathematical structure of the phase transition in a Floquet CFT, driven by SL2 algebra. Then you may ask, okay, now you have given the phase diagram. So what is the detailed structure in each phase?
Sorry, why is that? How is that kind of behavior reflect in the entanglement entropy?
Oh, good. For example, in this oscillating phase, when you calculate the correlation function, because the operator will always come back to the initial position after some time.
Okay.
Then when you calculate the correlation function, you can find it always oscillate in time.
Or you're using this defect operator. You're using
twist operator.
Twist operator. Yeah.
Exactly. But for this one, the operator will flow to a fixed point, and it will never come back to its initial position.
Mm-hmm.
Yeah. And if you calculate the correlation function, you can find that it decays exponentially, and the entanglement grows linearly.
I see.
Yeah. So, yeah, this is simply the phase diagram. What is the detailed feature in each phase? Okay, so later in this paper, in this paper with
So this is for the Möbius entropy.
Von Neumann entropy.
Yeah, but do you know how the Rayleigh entropy?
Yeah, sure. We could do everything. Rayleigh entropy is simply the coefficient difference n over n minus 1.
I see.
This is different from the diffusive system you introduced. Okay, if we look into the energy density distribution, we can find some very interesting feature. If we, in the non-heating phase, as we drive the system, the energy will not grow, which means the system doesn't absorb energy. But in the heating phase, as we drive the system, we have found that the system will absorb energy exponentially in time. What's amazing, the system does not absorb energy in a uniform way. There are two peaks in real space. This is real space. There are two peaks which grow exponentially in time. And in another paper, this one, this study exactly the same setup. This is the real space x. This is time t. The color means the amplitude of this energy density. They found, indeed, as you drive the system, there are two energy peaks formed in the system. This one is a numerical simulation based on some XXZ. Indeed, we observe the formation of two energy peaks.
Is it 2 peaks because you're driving with a sign?
Yeah, because we're driving with a
The
sign.
periodicity of the sign determines the position?
I mean, yeah, you can change your function f. If you change it, the precision, the precision of the two peaks depend on t0, t1, the driving period. If you fix the Hamiltonian, sure, if you change the Hamiltonian h1, the precision will also change. So the conclusion is, as long as you are in the heating phase, there are always two energy peaks.
Even if I'm driving with some analytic function, not just sign?
Here we simply consider sign. For arbitrary function, we
You'll have just everywhere. It will be everywhere.
Yeah, for arbitrary function, I don't know how to solve this problem. But I will give some discussion. Okay, now you see two energy peaks, but there are more amazing things underlying these two peaks. First, you can find that one peak is chiral, the other is anti-chiral. What do I mean? If you stop driving the system, you can find, this peak move in this way, this peak move in the other direction. They will simply, they are moving like solitary in the system. Another interesting thing is that all the entanglement.
Sorry, if you do the driving, they just stay in the same place?
Yeah.
They just stay in the same place. They don't change with time at all?
Yeah, what I mean by staying in the same place is that we only observe the system at the end of each driving here.
Oh, I see.
If we only observe the system here, the position doesn't change.
Right.
Sure, in between the two, they will move.
Do you know the behavior?
Sure.
Okay.
Yeah, we know the behavior. For example, after each cycle, they will switch position. Yeah. Okay. Another interesting feature is that all the entanglement are between these two peaks. I mean, as I mentioned just now, the half system entanglement grows linearly in time. They are all contributed by the entanglement between the two peaks. As we drive the system, in each cycle, we are pumping the EPR pair to the two peaks. So this is why I mentioned there should be some wormhole-like structure if we have a gravity due description of this setup. Okay. Also, the driving will amplify everything. What do I mean? If the initial state is chosen as the ground state, if you throw some operator in the initial state, this driving will amplify this effect. For example, if you throw a spin operator with a spin h bar, which are not equal, and you drive the system, you can find that the two energy peaks are are not the one is higher, one is lower, which are proportional to the conformal dimension h and h bar. Also, we also found some amazing relation. The total energy of the system is proportional to the central charge times exponential of entanglement entropy. So because entanglement entropy grows linearly, so the total energy always grows exponentially in time. You may ask, how universal are these features, including the phase diagram, the energy peak, and so on? Because till now we only studied the SL2 algebra driving. Our final goal is to study the Varasora algebra.
So is there any simple reason for that energy and entropy relation?
No. 5 minutes. Yeah, we don't. We simply observe this result, but we don't fully understand this result. Yeah. So, and the conjecture for the general Varasora algebra. So we have conjecture, which is we have partial proof. So the heating or not of the system only depends on the existence of fixed point on the circle. If there are fixed points, the system will always be heated. If there is no fixed point, the system will not be heated. For example, we can prove this is a sufficient condition of heating and not heating, and we haven't proved it is a necessary condition. This is still under proving. It seems that I don't have enough time. I will use 2 minutes to quickly go through the generalization to quasi-periodic driving. Quasi-periodic driving, simply, let me tell the result first. For the periodic driving, there are 2 phases. For the quasi-periodic driving, there are also 2 phases. But the phase diagram in the quasi-periodic driving is very interesting. There's some fractal structure. In the random driving, we can find there's only one phase, which is called the heating phase. We can prove this result. This is the proof is almost the same as 1D Anderson localization. In 1D, there's only localized phase. Also, in the random driving CFT, there's only heating phase. We can prove this one, but for the quasi-periodic one, we only have some numerical calculation, but we don't have any proof. In all these 3 cases, the heating phase only depends on the Lyapunov exponent of the product of the SL2C matrix. Okay, I will quickly show you the general feature. In the quasi-periodic driving, we still have 2 phases, the heating phase and the heating phase, but there are some fine structure in the entanglement entropy. There are some, because it is quasi-periodically driving, there is some irregular structure in the entanglement entropy. And
What do you mean by quasi-periodic?
Oh, good. We drive the system with, for example, we have 2 sets of periodical, one with period t, the other with period t prime. The t prime is square root q times t. Then we add them together. So there's no period anymore. But yeah, it is close to periodic case, but with no period. I will not mention. Yeah. So the phase diagram is quite interesting. There is some fractal-like structure in the phase diagram. It has some interesting pattern. Okay, I haven't don't have enough time. For the random driven CFT, we have different kind of random driving, but no matter what kind of random choice you choose, the system will always be heated up. In particular, the entanglement entropy will always grow linearly in time for the random driving. We can prove this result. The proof is actually based on some theorem in mathematics called the Furstenberg-Kasten theorem. Well, what I want to mention here is this book is a mathematics book. All this book is talking about the product of random SL, NC matrix. There are many interesting theorems in book, I found many of them can be applied to the random CFT. So I'm going through this book theorem by theorem and apply it to the random driving CFT. But this one is the most important one, which told us there is only one phase called the heating, which I call it heating phase. From this theorem, I can get the conclusion there's only one phase, heating phase. The entanglement entropy will always grow linearly in time. The total energy will always grow exponentially in time with this theorem. Okay, that's the end. So the open question is we want to work out some generalizations, like we add some non-integrable difference perturbation, some driving beyond SL2, some general initial state, other kind of driving, because the function f we choose can be arbitrary, can be of other form. Also, we want to know how to cooling a CFT. If the CFT is a finite temperature, for what kind of driving the system can be cooling down from low temperature. We also want to understand some holography view of this Floquet CFT, because this setup works for arbitrary CFT. There should be some holography view, and it's also interesting to study the higher dimensional CFT. That's it. Yeah.
So in the heating phase, is the entanglement growth universal, or is like slope of it? Is it universal or is it dependent?
Universal means
dependent on some central charge only or something?
Yeah, depends on central charge and the T0, T1. But and I mentioned for arbitrary parameter in the heating phase, it always grows linearly. But the coefficient is not universal.
Oh, okay.
Yeah, the behavior, linear T behavior is universal.
Okay. And if you consider like different drives, like instead of modulating the density profile of H0, but you drive with say L1 or something else, like a different version. Like if you do a drive with a different operator, can you analyze the same thing in this framework?
Yeah, till now we can only drive it with L0, Ln, L minus n.
Okay.
If you add Lm, L minus m, we can also study it. We also have some results. There are also only two phases.
So I have a couple of questions.
Yeah.
So first, how meaningful is it to compare all of this to, let's say, XXZ model? Because you're saying that energy is being absorbed exponentially.
Yeah.
CFT is usually just a low energy theory.
Oh, good. For the numerical simulation, they cannot drive it in for very long time, because the energy will go to high. If the energy is too high, it will break the conformal.
So it's a very short time.
Yeah.
Because can you go to the slide where you wrote the H0 and H1 in the very beginning, the Hamiltonians? You just okay. This is it possible to look at H1? So there's this formula for H1, right? Can I just say that this sign is the square root of G, and say that it's the same CFT, but what I am actually doing is I'm just changing metric in time?
Yeah. It is like changing the metric, the spatial, the metric in the time direction.
So then why is it important? Why can't you do it for any function? Why is it important that it's sine?
Oh, this is simple. Because for this choice, this is the simplest one. We can generalize we are generalizing to arbitrary function here. Yeah, this is the simplest one.
Do you assume that CFT is unitary?
The CFT is unitary. Yeah.
You use this.
Unitary. Yeah.
But what determines the peak?
Oh, the
The location of the peak?
Yeah, okay, good. The location of peak is determined by the position of the fixed point.
Oh, okay.
Yeah, where is the fixed point, then the peak is totally determined by it. And so the position of this fixed point is determined by Q0 and Q1. Yeah.
Okay, let's thank Xueda again.